Greetings. So this one we will consider some beam. Let's say the beam is something like this, and it is actually supported and has some forces applied to it. And concretely, there will be some two-value support at this side. I'll call this A, AX, and AY. And then on the right side, we have some one-value support, BY. And then in the middle there is, and what it means, one value, two value support means how many forces, reaction forces are behind that support. So this is something connection that holds the beam on this side in place, and it not only prevents it from vertical translation motion, but also from horizontal one. But the BY would only prevent it from vertical one. But when we already have horizontal here, it's determined that way. It's not going to move as a whole. And okay, so now we've taken care of the reactions, and then there's also going to be some two forces. Let's say we have a force pushing from below here, and it is 2 newtons, and then here we have 3 newtons from above. All right. And the distance between each of these segments is, this is always 1. So this is 1, this is 1, this is 1. So we have a beam of total length of 3. Whatever units those are. Let's say meters. So 1 meter this is, then, wow. Yeah. This part is also 1 meter between the 2 and 3 newtons. And this one is also 1 meter between the 3 newtons and By. All right, so this is the situation we have. And what I want to draw is the so-called shear moment diagram, which takes into account the shear forces along this beam. And yes, it's viewed from this side as a 2D thing, and it talks about shear forces, which are basically the forces perpendicular to the axis of the beam. So we have the beam like this is its axis, and then these forces are vertical, perpendicular to the beam. So those forces are perpendicular that have influence on the beam's total stress levels, so shear forces. And those are in general denoted as, for example, V. And then we have, then we also below that we're going to draw a moment diagram, which takes care about the moment at each point of this beam, throughout this beam. And so we can start with that once we have determined the reaction forces that we will need for this. And just to make this clear, yes, in a general scenario, it's logical we have this AX here as well. But because I'm going to be talking about shear forces and moments, and these moments will be caused by the shear forces and not directly by these so-called forces acting in the direction of the beam. For that reason, the forces like AX, we don't even have to determine. And actually, AX in this case is the only force in parallel to the beam. So what I'm just saying here is that we have some support reactions to figure out, right? We have these 2 newtons, 3 newtons, that's found out. But AY and BY have to be something. And when we're looking for them, we won't have to care about AX. So we're looking for the Y direction forces. So first of all, before I start with everything, I should find the values of AY and BY. So what are those going to be? I'm going to respectively use, well, what I can do is take a moment around A and then calculate thereby for B. So I will take a moment at A, and that should equal in total to 0. So the net moment at A should equal to 0. And then what do we get from that? Well, it is AY, AX are not going to be counted into it. AX will not be counted in any case because we're taking the moment around this point and the AX goes straight through it. And also it's not causing a moment because it's not in the direction that it would cause a moment. The total direction that causes the most moment is one that's perpendicular to the beam from this perspective. Alright, so the first force we're taking into account is the 2 newtons. And it acts in this direction, which counterclockwise is counted as positive, so 2 newtons times the distance from it, so 1 meter. Then I continue here. I add it, and 3 newtons, but it acts in a clockwise manner, and clockwise, the forces that cause clockwise rotation are counted as negative. So minus 3 newtons times the distance from A, because I'm doing total moment A, that's 2 meters. And then the last part is By, and this one is positive because it's a counterclockwise moment causing. And so By times the distance from A. And now that I got that, I can solve for By directly. So this has to all be added. So how many newtons is By gonna be? 4 Newton meters, taking care of these ones, is By times 3 meters. So 4 Newton meters over 3 meters is By, and that means that By is 4 over 3 newtons. Alright, so we determined By, 4 over 3 newtons. And now I can use the total equilibrium in Y, forces being equal to 0, and directly get Ay. So Ay, the ones that are up, I'm gonna count as positive. And so before it might have been a little different, but now the ones that are up are counted as positive because I'm talking about the sum of forces in the Y direction. So the ones going up are positive and the ones going down are negative. So what do we have? It's Ay going up plus 2 newtons minus 3 newtons because that's going down, and plus 4 over 3. We got the By already, and that's going up. So all having to equal to 0, and then Ay is going to be minus 2 newtons plus 3 newtons minus 4 over 3 newtons. So I isolated Ay on one side and everything else on the other side. So what I have from this is Ay equals to 1 Newton minus 4 over 3 newtons, which is like 4 over 4 newtons minus 3 over 3 newtons minus 4 over 3 newtons, and that's minus 1 over 3 newtons. So that means that Ay actually the direction I wrote here is wrong, and yes, I can write this as minus 1 over 3 newtons and have the arrow up, or I can switch the arrow and write a positive variant of this. There's this idea. If the result ends up being negative, that means that I can switch the direction of the drawn force, which I will do. So instead of saying, well, what would happen here in the equation is, I could have also drawn the Ay going down straight away, and in such case, there would be minus here, and everything would be different, right? And now, yes, that would actually be right. So now, if I switch the arrow going down, everything is flipped, and so Ay is directly equal to positive, because it's denoted as going down, is equal to positive 1 over 3 newtons. And I can also check this via the method of using a moment around, for example, B. I can do that, and we can show that the result is going to be the same. But I saved some time by doing the equilibrium only in Y direction. Alright, so that we got out of the way. And so now we have all the support forces in the Y direction. That's what we need. And also we have the forces applied throughout the body in the Y direction. And then to draw a shear moment diagram, create some vertical lines, and then create two graphs respectively. And in this example, I'll show you the rules on how to manage this. So I first draw a graph for the shear forces. So shear force diagram denoted V. And if I imagine there being some x-axis that goes from here, starts at 0 and goes to the right side, then I can say this is a V of x, as x starts from 0 and goes to the right side, right? And this is not necessary, and usually it's not even mentioned like this, drawn here. But in any case, and also the V I don't have to write as V of x, we could make it simpler and in a graphic method. But also we can, in a second, mention some connection to derivatives. And so, the idea here is that if I have this beam here, the shear diagram will take into account all the forces, and we will make a jump in the value of this graph, every time there is a concentrated force, which there is this one, this one, this one, this one, and at the end of the day, we should start at 0 and also end at 0. So, well, we would start at 0 if this reaction was not right at the point x equals 0 in the start, but here, because we have this force jumping down, we will start at minus 1 over 3 Newton because it goes straight down. So, the idea is, if we have simple forces like this, I will start at minus 1 over 3 Newtons because this force, this first force, makes it go straight down to minus 1 over 3 Newtons. And then the graph will be linear and nothing will happen until some other force hits. So all these things will be directly translated to the graph below. This is the first one to which it's translated. I just will create these vertical lines to make sure that we are synchronized visually. And yes, this beginning should also be at the same point. So this is the idea. And this 1 over 3 Newton going down made it go straight to minus 1 over 3 Newtons. This is the 0 height. Then we continue until when another force hits. This one goes 2 Newtons up. So I will jump by 2 Newtons up. Minus 1 over 3 plus 6 over 3 is 5 over 3. So we have 5 over 3 Newtons here. Then I continue further until I hit the next force. That goes 3 Newtons down. So that's 5 over 3 minus 9 over 3. So it's minus 4 over 3. Yeah. So the value should be, I'll trace it, minus, so it was 5 over 3 minus 9 over 3 minus 4 over 3 Newtons. So we got here. And then again, I continue until I hit another force. And this one is 4 over 3 up, so it takes me back to 0. So that's as expected. So that is what was supposed to happen. To start with something and then end up at the value of 0. So this is the shear diagram. The shear forces influence the graph like this with jumps. So basically this is a constant graph with a derivative of 0 all here, 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 here. And then there's these sudden jumps between. So we got that. And this is also precisely caused because we have just concentrated loads, concentrated forces at one point always. There's more complicated examples that we might go in another one, where, for example, already in V there is some linear tendencies of the forces or even some other shapes of the graph because the force is not applied immediately at a point and doesn't influence the graph with jumps, but it influences it gradually. So the value will even change on these things. So there might be a linear segment, even linear still, but it will not be constant, but it will be at the slope, for example. But we will get the slope in the moment diagram in a second anyway, so we're going to see part of it anyway. So this was the shear diagram, and then we draw the moment diagram. So the moment diagram is, again, a similar idea, but the point is that we take the integral of this in order to get the moment diagram. So in this case, what it means is I can always calculate the area between the curve and the x-axis, if this is the x-axis. And so the area between the curve and the x-axis will be the accumulation, which would be denoted by those integrals of these individual parts. And that is what will be contributing to create the moment diagram. Alright, so what we have here is, I will start at 0 by default, and there are also some things called concentrated moments, and those would influence our graph for the moment. So this graph, so this was V, but this is another graph, M, for the moment diagram, but it's straight below this previous diagram because we have this connection. But there's something called concentrated moments, and if we had them on this beam, then those would influence the graph with the same kind of jumps that these point forces influence the V diagram. But we don't have concentrated moments, so there won't be such big jumps on this one. There won't be such jumps on the M diagram in this case. Alright, so again, we have M and it goes along this x-axis somewhere until the end of the beam. We follow the length of the beam like that, straight below it. And now I can calculate the areas of these individual parts. So it's actually simple because we said that each of these segments is 1 meter long. So the area here is minus 1 over 3 Newton meters. Newtons times meters because meters times newtons. I don't have to do the unit, I could just write the magnitude of the area. In any case, then we have 5 over 3 newtons times 1 meter, so it's 5 over 3 Newton meters. And then down here, we have minus 4 over 3 times 1. So minus 4 over 3. And you can see that if you add all these up, you get, in the end, 0. These three values add up to 0. So that means that the integral of these parts that this moment diagram is basically will end up at 0 value in the end. And we won't have any jumps, as I said. There's no concentrating moments, those small round circles with arrows that would denote like an immediate moment at a certain point. That's not in the case of this beam. So that's not to be taken care of, but the effect would be the same, like there was an effect with these forces on the P diamond. Alright, so we can start. So I start at 0. And what I basically want to do is I want to use this and integrate it. And because these all are constant things, then the integral of it will be a linear function with the slope of the constant value of these respective parts. So the function for m on the interval from 0 to this one will be minus 1 over 3, but the integral of it, so minus 1/3 x. So something like this. And so we get 2. Eventually, after 1 unit, we get to minus 1/3. So that's very useful. That this graph is a very nice example because there's 1 meter, 1 meter, 1 meter. Not big calculations are needed. And actually, the values will be we'll get to the same ones. Then we have an integral of this one again. So for this segment from 1 to 2, we need an integral of what is the accumulation, basically the integral of this function of the 5/3. That's y equals 5/3. Or in other words, we want to cover this accumulation of this block above the x-axis. The integral of it is 5 over 3x, and if it's taking place for 1 unit, it's going to get us linearly, because it's 5 over 3x, a linear function at slope 5 over 3. It's going to get us to 4 over 3 to 4 over 3. And then, in the end, we have minus 4 over 3, and again, integrate it, you get minus 4 over 3x, and that continues for 1 unit. That means that there is going to be a linear function sloping down at minus 4 over 3, and after 1 unit, it will exactly hit 0. So we see the moment diagram is made up of integrals of these individual parts of the shear diagram, and it ends at 0 like this. So that was an example of this, and in some next one we might go into some examples also with the normal force diagram or something like that. But for this one, this was an example that shows the general principle, which is based on having a beam, having some forces applied to it, also first of all making sure we have the reaction forces in the y direction to get the shear diagram, and then from the shear diagram as an integral we can directly derive the moment diagram.